Hello everyone and welcome to the next episode of my response to Flatzoid, this time number 2, Natural Laws and Gravity. Originally I intended to make 2 separate videos on the topic, but I thought, whatever, the natural laws thing wouldn't have been worth a whole video, so I just thought I included it in here. Now, about the natural laws, Flatzoid has said something in his response that is so fundamentally wrong, I just had to address it. There were a couple of things in there like that, some of which I will make a video about, some of which I don't think are worth my time. My favorite highway is natural laws aren't part of science, which is fun. Originally, we in physics don't even refer to them as natural laws, we call them scientific laws. I wonder why. I have 3 definitions here, one from Wikipedia. Scientific laws, or laws of science, are statements based on repeated experiments or observations that describe or predict a range of natural phenomena. I completely agree. From LibreText's the chemistry course, kind of a scientific law is a statement that summarizes the relationship between variables. That's a very short and concise one, more oriented towards mathematical formalism behind the whole thing. I still agree though, in physics or in chemistry you can absolutely say that. And as a more general rule of thumb, I have one down here from the Kansas State University biology department. They say that a law is a set of observed regularities expressed in a concise verbal or mathematical statement. Within physics, they are pretty much all the time mathematical, although you can, of course, rewrite them, if you will, or formulate them out into some sort of verbal thing. So very much all of those are part of science. Flatzoid and some other flat earthers that frankly don't really know what they're talking about like to say that science only deals with stuff that sorts out the cause and effect. Could you show me one scientific law that doesn't do that? Just one, within physics, for example. If you look at Coulomb's law, it very much deals with cause and effect. If you look at Newton's law of gravity, which is a natural law, by the way, it deals with cause and effect. I am absolutely lost as to how you could say that natural laws aren't part of science. Presumably without asking an actual scientist about it. Because we would tell you that you're just wrong, but I guess you're used to that. So I have to summarize the very obvious here. Scientific laws are part of science. Who would have thought? Now that we got that covered, let's move on to the whole gravity thing that Flatzoid in his last live stream, where he addressed my criticisms of how he uses entropy. He said that why are we having this discussion anyway? Gravity still can't overpower, I believe he said, entropy, even though entropy is still a quantity, not a process, but so Flatzoid formulated it this way: gravity can't overcome entropy. I would formulate it in another way. I would say that something that is, to Flatzoid, not a force, cannot have a stronger effect on gas than what a thermodynamic law predicts. I think that is a more scientifically literate statement of what Flatzoid tries to say. First of all, this is not how physics works. A law doesn't say that this happens, period. A law says that, for example, let's go back to Coulomb's law. A law would say that the force from electrostatics or from the charges of the particles is laid out in the way that Coulomb's law says. It doesn't say how it moves, it doesn't say anything, it just says that that's how that works. Ohm's law says how the voltage, how resistance work together, and you can use that to calculate for the amount of current, or you can rearrange it and do anything else you want with it, right? By the way, all laws have very well-known ranges in which they work. Ohm's law doesn't take into account the fact that the conductivity of materials change with the temperature, for example. Newton's law of gravity, of course, doesn't know anything about the curvature of space-time. So all of these laws have limits, by the way. Okay, so going back to this statement, when Flatzoids says that gravity can't overcome entropy, first of all, this is not how physics works. Just because you think that like the second law of thermodynamics says that it goes to a maximum, you don't actually know where the maximum is. Gravity acts as a sort of restriction to where the actual maximum lies. Also, gravity is a scientific law, the law of gravitational attraction. So what you're really doing here is you are saying that second law, like the law of gravitational attraction, cannot be stronger than the second law of thermodynamics. So you're essentially cherry picking here, maybe to confirm a belief. That's just what I would guess. Next thing here is that entropy takes on the maximum of the system, but you don't know what this maximum is. The system has restrictions, it has constraints. The second law of thermodynamics, taken at face value with the two containers, is the simplest possible system that you can have, right? Earth is not that simple of a system. There are restrictions in place. And the other thing, as stated in another video, entropy is increasing anyway. So when you're saying that entropy has to increase, well, it is. What are you complaining about? It is increasing as we speak. Right now, the entropy of the system Earth space is increasing. That's just what's going on. And I fully expect Flatzoid here to play the presentation of the gas filling the tank. I will cover that in a bit. Actually, I will cover it right now. We have a pressure gradient. You know that. You have tried to explain where the pressure gradient comes from. You say that it comes from the ideal gas law. I would love for you to actually write that out in a mathematical way, because the few explanations I've heard from you were very poor and just not even in correct scientific language. So I'd urge you to formalize them a bit. So essentially what I'm going to explain now is how the pressure gradient that we can measure absolutely confirms the way that we think about gases. So you have pressure on the one hand from collisions with other molecules that will push your particle upwards, because the pressure upwards is lower than it is down, so it will the pressure gradient points upwards. And you have something that pulls you down, that is a downward acceleration from gravity, whether Newtonian or Einsteinian. Both will pull you down. Now, Flatzoid, I hope you actually do the thing that I do now. You will now say that, but gravity isn't a force. I will show you a clip from a video that I did about 3 months ago, and let past Olaf explain. So Flatzoid wants a citation that Newtonian gravity is a consequence of Einsteinian gravity, and I shall bring it. So here I am back with my citation, and my citation actually is the book by Piotr Kruszczyl, who is a professor for general relativity and cosmology and gravitational physics, actually, gravitational physics. This is his book, Elements of General Relativity, that we use in our GR course at our university. And I would like to briefly introduce you to the Schwarzschild metric. You do not need to understand any differential geometry for this, because neither do I. The Schwarzschild metric is an approximation, right? It's an approximation that you have when you have one central kind of origin of gravity, if you will, one origin of curving space-time, really. It is called here a black hole solution, because the black hole is the epiphany of this concept, right, where you have one massive gravitational source in the middle with nothing else around. The Schwarzschild metric is for one source of gravity and for very little other stuff around, which is actually pretty much what you can approximate Earth as, right? It's not an exact solution, but it's approximative enough. And here, when you go through a whole bunch of mathematics that is pretty complex, here you would have the flagship example, so to speak, is the Schwarzschild metric. I cannot explain sadly within the limited time and honestly limited mathematics that my average viewer will understand what this is. Also, I don't fully understand it myself. What I can, however, show you, especially to you, Flatzoids, should you ever see this video, please remember that I will show you now the acceleration here, which is a 4-vector, and it is defined as something, and then you can calculate it within the Schwarzschild metric, and the 4 acceleration can be found to be the mass of the central object divided by the radius squared times this delta r here. Note that this is not a derivation operator or anything. This is just a unit vector, so a vector of the length 1 pointing to wherever the mass is. This is the center of mass is, right? And this is the acceleration. So really, if you were to figure out the gravitational acceleration from Newton's law of gravity, it would be big G times m over r squared, and you can add a vector here, unit vector, that just points in the direction if you want to have it in a vectorial form, right? So this would be that. So in the book about elements of general relativities, which is supposed to be an entry to general relativity, it says very much that you can get the Newton's law of gravity from Einstein's tensor equations using the Schwarzschild metric, which is an approximation that is very reasonable to make for the Earth. Exactly. Thank you, Pastor Olaf. Now, what can we say from that? The text is supposed to be in front of it. So what I wanted to say here is that actually there is an acceleration either way. Both in Newtonian and Einsteinian would predict an acceleration for the gas molecules downwards. So I'm going to use it. So Flatzoid. Also, I'm so sorry. I don't know why the video is always in front. I actually had a screenshot here from Flatzoid. I hope you can see it. Under the video that I did about that. That's how Flatzoid became a subscriber of mine when I did this video. So he knows that. He has seen this citation before. So that's what I find funny. So with that, let's continue. We have again an upward something pushing you up with the pressure and something pulling you down. It's the acceleration. Now I'm sorry for the math. I'll briefly brisk over it. We start with the ideal gas law. We change it to the molar form with density in there. By the way, Flatzoid said that you can't increase density of a gas, which, you know, a person like that really shouldn't make any claims about ideal gases. Now we take the hydrostatic pressure formula. Note the color coding here. Everything that has that kind of arises from gas physics is colored in this light blue, and everything that arises or has something to do really with gravity comes from is colored here in this orange. So we have the change of pressure, like how high pressure is down here at the surface of the Earth, is just this thing here, which is essentially the gravitational acceleration, the density and how much of it you have. dH is here an increment of height. We divide those two. So now the first of all, the densities are cancelling out. And actually, I would like to notice that here, scientifically adept people, like people with maybe that have made extensive high school maths or that are at the start of the university, will have realized what to do with this equation. So Flatzoid, what happens here? What can I do with this equation to get P out of here? This is dP. That's a differential kind of a differential P here, an increment of P. What can I do with it? Well, you can integrate, of course. If you integrate it here, I stopped the color coding here because it's not relevant anymore. With the integration, you get a formula, the barometric height formula, after the integration, which is here, which is the pressure that you measure at a given height, which is here Z. The pressure at a given height is the pressure at 0 times e to the minus mgc divided by RT, where RT over mg is the so-called scale height, the height at which the air pressure has decreased by a factor of E, the Euler's number, which is about 8.3, 8.4 kilometers. The thing here is that this depends actually on how much the temperature varies with the height, which is a whole other can of worms, but you know, it's not straightforward. However, we can make the simplest possible approximation. Usually what you do from this step to this step, by the way, is you have to take into account, as I said right now, the how much the temperature changes with height, right? You can say that you are losing somewhere between, I believe it was 7 to 10 degrees per kilometer, I believe it was. Something of that sort. I'm not entirely sure. Don't take this at face value. This is just something I remember. So really, you should take this into account. But the simplest possible solution is assuming that the temperature is a constant, which is not, but it still gives good enough results, right? So I live at roughly 510 meters above mean sea level. So from that and from this formula, plugging in the scale height with 8.4 kilometers, I would expect an air pressure where I live of roughly 95,400 pascals, right? So this is a prediction that I make. Unfortunately, I do not own a barometer. Oh wait, I own a barometer. Well, would you look at that? So I don't know what there's stuff here. I don't think there should be. I hope it's not in the recording. This is my recorded pressure because I actually own a weather station that I built and programmed myself. This is the pressure here over the last 9 hours. And you can see that this is the theoretical pressure that I would expect. It is roughly below 95,400 pascals. It's 95,380, I believe. This is the theoretically calculated pressure, and this is the pressure that I actually measure, which varies due to weather and sometimes due to temperature and stuff like that. But that is still a very good approximation. With very little mathematics and with essentially just with one formula, I could tell how high the pressure is at the place that I am right now. And I was correct within, would I have done that 3 to 4 hours ago? I would have been spot on. But right now we're about, let's say we're 300, maybe 400 pascals away, which is very little. That's really little. So yeah, I would argue then that this formula, and I want to emphasize this formula was derived using only the ideal gas law, which is wrong because no gas is ideal, and only the most simple of gravitational considerations. That's it. That's all you need. And you get an accurate prediction. Yeah, so Flatzoid, right now, can you make a better prediction? Until you can, our model definitely wins, and I didn't even try to make a good prediction. This was the simplest possible prediction I could have made. I did not use some real gas laws. I did not include the temperature dependence on height. I did not do any fancy gravitational math, and we are still almost bang on. Can you do a better prediction? Until you can, honestly, you have no place at this table of debate because honestly, you clearly don't know what you're talking about. Do you think that this is a coincidence, what I did here? You can derive it using only principles of classical mechanics and pretty simple gas physics and some fancy math, I admit. But not even that fancy, but fancy for a layman. Do you think that this is a coincidence that it works when I include gravity? Do you really think that? I don't think it. So, challenge for Flatzoid here. Come up with a better derivation or equation, and thus equation for pressure that does not need gravity to take it into account. Or alternatively, you have to acknowledge that you're wrong. And with that, I thank you very much for watching. I hope you did enjoy this video. If you did, please consider leaving a like if you enjoyed it a lot. I would highly enjoy it if you considered subscribing. And with that, I will wish you a nice day, and I hope I can see you in the next one. Goodbye!